Anyway, all right, let's go. Right, so here's what happened, right? So if you remember, anybody remember how this view light? That what type of properties light has?
Right.
Light has what type of properties? And moving a straight line, all right, and whatever properties is that? It's linear, no? All right. So light initially, they thought light behaves like waves only. Right. But light really behaves as a wave and a particle. This experiment that we're going on today basically shows you how they went from wave only to wave and particle. All right. So here's what we're looking at. Right. Actually, there's a nice little small simulation we're doing, which is fast, right? And we'll observe what happening here. Right. What you see? All right. So it might be a little, where this thing is, right? That's not what they're trying to stop it. Oh, wait, if you online, you're not seeing anything. Online, what you're seeing? That's not something wrong here. Online, what you're seeing now, what you're seeing on the screen now. How much time I take return to online, you're seeing anything? Something wrong, right? All right, I'm not sure. I'll go back to it after and see, right? I'm not sure why I'm not sure. Right, so what you see here? Here's what the photoelectric effect is, right? Let's say I gave you a metal. Let's say, Dylan, let's say this is a metal here, right? Right, of course, the metal made up of atoms. And within these atoms, you have what? You have nuclei and you have free electrons, right? So let's pretend the X's there are your free electrons. I went a little small there one line, but you should be able to see it, right? These are the X's, right? here's what the photoelectric effect is, right? The experiment was I had metal, and then I took radiation, and I allowed the radiation to hit the metal. When the radiation hit the metal, provided the radiation had specific conditions, when the radiation hit the metal, the electrons, those electrons left. Those electrons, they left the metal. Let's call them photoelectrons. Let's call them photoelectron. So here we have incident radiation. When the incident radiation hits the metal, electrons leave it. That's okay? That's okay. All right. So what's that there? So here's the problem, right? You have to be able to explain it, right? When the incident radiation hit this, electrons leave it. The problem is, back then, classical physics couldn't explain it. Classical physics could not explain everything that happened in there. And then they came up with a new branch of physics called this is the era that we live in. We live in the modern era of physics. So because of this experiment, they went from classical to modern. Right? So classical is where they taught light. What other man is do that, boy? Not pay attention and know these things. Right? Classical is when they view light as having been waves only. And then modern is where we introduce the concept of particle nature, duality. Right? Nice. So what happened here? So here's what happened. During the experiment, a few things happened that classical physics couldn't really explain. All right. So the first thing that happened is that they thought, right, when the radiation hit there, the electrons would have had to gain energy, then break the bonds, then leave. But that didn't happen. They recognized that the electrons left instantaneously. So as soon as it hit, as soon as the radiation hit, electrons leave immediately. They couldn't explain that. They thought it would have built up and then leave. Then, here's what also happened. They thought that if they increase intensity, if they increase the intensity of the radiation, then that would equal to an increase in energy of electrons. That didn't happen. Right? What does increase in intensity mean? An increase in intensity simply means that instead of 2 radiation, you probably have 3 or 4 or 5 more radiation. That's okay? Yeah? And here's what made it even worse. They recognized that when they increase the frequency, then they recognize when they increase the frequency of the incident radiation, they recognize that, well, wait, why is this increasing the energy? They recognize it increased the energy of the electrons. So intensity, no effect. Frequency, the required effect. Are you okay with that? Yeah. So by changing the frequency of these waves, they recognize that the energy of the electron went up. And lastly, an increase in intensity only increase the number of electrons leaving. Right? So if I had, I just say, if I had 2 radiation, 2 electrons leaving. If I have 3, 3 electrons. If I have 4, 4 electrons. Technically. It is technically one. That's okay? So those were the four things that happened in the experiment, but classical physics was not enough to explain that. Right? So who came along? Einstein. Einstein came along now and proposed. So Sylvester came along and proposed that here's what. We can't keep giving light as waves of this. We have to introduce a concept called particle nature, or what we call photons. That's okay? Right? Because here's what they thought. They thought electrons would take a while to leave. They thought intensity would increase the energy. That didn't happen. They thought an increase in frequency will have no effect on the energy. That didn't happen. They thought, well, this was kind of right. They thought that the increase in intensity gave you an increase in electrons. That happened, right? But they couldn't explain these things.
Out of everything, one thing was correct.
Technically. Right? But technically this was wrong because they thought intensity would have changed this. But instead, intensity changed this. All right? Are you okay with that? Right? So here's what Einstein proposed. Einstein proposed concept of photons. Right? Einstein proposed concept of photons, right? So if you want to write this down, and I'll start to explain the next part after. So I know someone can't take more than 5 minutes to explain.
So yeah, that's how the for this much there are only differences.
What? Yeah.
Oh,
I'm examining it here. Copy down.
What they expected, what they was expected. What the stations what? Yeah, at least maximum videos. I don't No, bro, you know what? What the hell? As given a crown, you know, as given a crown, but don't have a box.
Now.
I get think that's big Israel.
Right, so we need to be able to explain why all this happened. Finish right? No.
So when in the exam, right?
Yeah.
When they ask you for what was expected, and what they got.
So they can ask a question, came already where they ask you what were the issues classical physics had?
Right. It gave us what happened, but it never gave us what they expected.
Yeah, and I tell you why. Anyway, it's in the handout, you know.
Okay.
All right, but these are the things here. These are the things here that that they couldn't explain. So classical physics couldn't explain those four things. Right? Now,
But I think I won't participate. Also, love to go on. So that's actually what they can't see.
so what I wanted to do here from is someone to finish. Let's explain what is the concept of photons is.
Yes, if you go shoot up that up, like that, I think I'll go. Yeah, you can do it. Yeah. Well, we've got school for the. So. Yeah, that's right. Friday. But I like this is Friday. That's something. I don't know. You agree? Is it? When you see from taking for 6 and I'm telling if you put it. Dario, don't be feeling concept. Somebody should go. Yeah. Because it's not right.
All right, let's go, right? You have to finish, right? You are known for the money. All right, nice. So here's how we fix all of this now. So here's what Einstein said. Einstein said instead of viewing them like light alone, instead of waves, what we could do is we could view them as particles that move in a kind of wave-like structure, right? And these particles here, we call them photons. Okay? So what he said is that these photons were equal to like little energy packets. And the energy of each of these photons is given by hf. It is a constant. I'll explain that in a little while. At F is frequency, right? So the energy of every single one of these photons was hf. So how did this simple explanation fix all of this? Number one, the only way we could think of, the only way that we can view packets is a particle nature, right? So we had to now move from light being waves to thinking about light as a particle. And every single one of particles has E is equal to h of energy. All right? Everybody okay with that? So watch this here. So in order for us to do this, hey, watch here now. Right? In order for us to explain all of this now, let's ignore the wave nature. Let's focus on particle nature. So imagine you have a particle hitting here, right? For the electrons to break bonds, what must happen? The electrons must gain energy to break bonds, right? So view it like this. Let's say an electron needs 2 joules of energy to break bonds right? Suppose the electron needs 2 joules of energy and a photon comes in with 4 joules of energy. What will happen? Will that be enough? Yes. That electron, let's use 5. Comes in with 5. The electron now will take the 2 joules of energy and what? It will break the bonds, but ended being hit with 5 joules.
Yeah.
So 3 remaining, right?
Yeah.
So then it will move away with 3 joules. So this is an instantaneous thing. Come in, enough energy, you can leave.
And
Wow.
it almost like really starts heat, right?
Right? And what would happen if it's 1 joule of energy? Nothing will happen. Right? So either they leave instantaneously or they don't leave at all. Everybody okay with that? Yeah? Cristiano, you okay with that?
So, wow, what's the difference?
Nothing, can't do anything. So if it keep getting hit with 1 joule of energy, it's not enough for the reaction. Energy just wasted and passed through the metal. So the metal might have to get warmer. Right?
So it'll be really starts heat, like I said.
Okay, yeah.
So
Right?
Like,
You wasn't correct at that point, so. Everybody okay with that? Everybody okay with that? So that explains number 1.
so
Yeah?
Was the way charge of
Huh?
so flying electron so
Yeah, it becomes an ion. So it'll become ion. Alright? Any questions online?
it's still
Now, how do I increase the energy now? What did I tell you that E is equal to what? HF. E is equal to HF, right? So E is equal to HF, right? I know you all don't know what is H, but H is a constant. It's called Planck constant. Planck constant. So what controls energy? If H is a constant. Frequency. You all seeing that? So if I increase frequency, I will increase the, and if I increase the energy, I'll increase the energy leaving with. Correct? If I increase this and this becomes 7, this will always be 2, but this now becomes very good. So now we know why this happened and we know why this happened. Everybody okay with that? Everybody okay? Last 2. Let us say, anybody can answer. Let us say I have light incident on this and it's supplying 1 joule of energy, but I need 2 joules of energy. If instead of 3, I have 4 or 5 or 6, will that change the number of electrons leaving? They come in with 1 joule of energy. No, right? Yeah? It don't matter if I bring 100 of them with 1 joule of energy, will electrons leave? So by increasing the intensity, I can't increase the energy. That makes sense? That makes sense? But let's say it was 3 joules and I only need 2. If I give you more, and more electrons will leave. So that one little concept there fixes this whole problem. You're seeing that? And the way to remember this is, I remember giving an example once. You want a maxi to take it to C3, right? And what do you remain money to go in the vape shop and buy some extra vape and thing, right? So let's say the maxi costs $10, right? If you go to the maxi, right, with $5, would you be able to reach C3? No. Right? No, not him. One.
Like next school?
Yeah, but tell them already. Tell me you put it on the elements.
No, that's next one.
No,
That one, the next one.
Right? But yeah. Now, but if you go to the, but if you go to the maxi and you had $50 and you tend to reach movie time, you reach movie time and you have 40 extra. Okay? And you can probably use that 40 now to go and buy a bill. Right? So anyway, so the concept is if you don't have enough, you can't let the electron will not leave. If you have more than enough, the electron will leave and the remaining is the extra. That's okay? All right. So what do you write? You can write the formula E is equal to HF. Right? And write this here.
Right?
Yeah, I'll just give you the same step. Time back our heart in the hand now. No, I'm just going through the explanation for each one. So number one, so you can put this in like a table, right? So I'm going to explain this here. So I'm going to explain how modern physics solves this problem. I'm going to explain how modern physics explains this one. So 1, 3, 2, and 4. 1 and 3 is the same explanation, similar explanation. 2 and 4, similar explanation. Online, are they okay there? Katrina, Kalina, are they okay? Mills, are they good? Everyone's here. Right, so write this here. What I want you to have is the explanation. So, number one, right? That's right here. Electrons left instantaneously. Electrons left instantaneously. Once the photon had enough energy, to transfer to the electron to break its bond. To transfer to the electron, sorry, to break its bond. Number 3, 1 and 3 together, right? 1 and 3 together. Remember 1 and 3 together, right? Number 3, an increase in frequency. Number 3, an increase in frequency. An increase in frequency. Increase the energy of the incident radiation. An increase in frequency. Increase the energy of the incident radiation. And hence has more energy available for the electrons. And hence has more energy available for the leaving electrons. For the leaving electron. For the leaving electron. sorry, put photoelectrons, right? Put leaving electrons slash photoelectrons. Leaving electrons slash photoelectrons.
See. No, Friday number.
Use a MATLAB.
Yeah. Yeah, I use the lights out.
Right? Explain number 2 now. An increase in intensity. An increase in intensity. This is to explain 2. An increase in intensity does not affect the energy of the photons. An increase in intensity does not affect the energy of the photons. What last thing I said?
Photons.
An increase in intensity. What's that?
Does not affect the energy of the photon.
And hence will not affect the energy of the electrons leaving. And hence will not affect the energy of the photoelectrons. And hence will not affect the energy of the photoelectron. Lastly, number 4, last one. Last one. An increase in intensity. An increase in intensity. An increase in intensity implies an increase in number of photons. Which in turn will increase the number of photoelectrons leaving. Which in turn will increase the number of photoelectrons leaving. If I can find out, let us know. Right, well, yeah. So here's what I need some help with, right? Pretend you are Einstein, I'm Sylvester.
Yeah.
I need some help here. Let's see if we could create a little formula now. Watch here. Let's see if we can create a formula based on the conservation of energy. Energy being supplied is HF, right? See if you can create a little formula based on what's happening here. You want to create a little formula based on what's happening here. A formula. Huh? Right, no. Don't go there as yet. Right, go easier. If you want a formula to explain what's happening here. Say it again, say it again.
HF minus D
HF
minus the square value.
minus the amount to break the bonds. Okay, let's use words, right? Let's use words and we'll put the values in there. So let's start here. Energy of photon minus energy to break bonds equal to the remaining energy for the electrons, right? Equal to the remaining energy of electrons. Right? Very good. This is the formula Einstein came up with. Right? Energy of the photon is what? HF. Right? This is something new, right? This is what we call work. As it right symbol?
Oh my God.
Just like pi. I can't remember.
That thing from Star Wars.
It's just like pi though. Anyway. This is the thing I'm applying, Max, to find the anyway. Right. Work function. This is called work function. And the remaining energy, the particles what?
Yeah.
How the particles how the particles leaving and moving away, right? So whatever energy the particle have connected. Right? So the formula is HF is equal to phi plus kinetic energy. That's okay? So phi is HF naught. I'll explain that. And kinetic energy, we know what that is. A half mv squared. Okay? So this formula here summarizes everything that we learned today. Let's see if this simulation will work now, right?
Yeah.
Huh? Yeah, this is fine.
Wait now. Genius of last Our answer correct. Yes, yeah, ma. I will go my share to my book without. Very nice.
Online, we all see it now. You're seeing the photo effect experiments.
Yeah. I don't see the pattern.
Online, you'll see the experiment there. Katrina? Yes? All right. So we look up here. You all can see the photo cell up here?
Yeah.
Right. Could you kind of explain what happened in there? Clear the graph. You can't pause this thing, you'll see pause anyway.
Right there.
Right.
Okay, right there.
Alright, let's start it.
So I just slow it down.
No, I was stop it.
So look on the board against those.
This is what we go go slow down.
Alright, so look at what happened in there.
Well, we put slow.
Anybody recognize what happened in there? What's the list? What's the list squibbly line? Radiation, right? And then the radiation, so that whole radiation altogether might be like one photon, right? Kinda, right? When the radiation hit the metal bar there, you see electrons leaving? So that means the photoelectric effect is happening. That makes sense? Why are we getting this reading here? 0.7 milliamperes. Why are we getting a current reading here? Because electrons flowing, right? And electrons leaving plate. Let's label the plate, right? Let's call this plate E and let's call this plate B. You're seeing that? So the electrons leaving plate A and going to plate B. Have I saying that?
Yeah.
So it means that the photoelectric effect happening, and because electrons moving, we ended up with what? We ended up with current, right? Current reading here.
What's that?
Current at amperes.
No, wait.
There's an arrow.
What's that?
Right? Right. So the electrons leaving A and going to B. What's this here? I am going to increase the intensity, right? Look at the graph right now. The graph, this is a graph of voltmeter reading versus current. So there is current and the values around 0.7. You're saying that? I am going to increase the intensity. What do you all expect to change there? I am going to increase the radiation intensity from 2 to maybe 4. What do you all think will happen? Current will go up. Let's see. See that? No, I said 4. Why don't change the what?
Yeah, change the color, change the color. Change the
Which
yellow
color?
something.
Here?
Yeah.
Yeah. That's not. We're coming today. We're coming today. Okay, well, excited to it. How I can make this? You sure? Okay.
Yeah, I'm afraid it's screen was right there.
Slow. Yeah.
Next city.
It's slow.
This one.
Yeah.
Wow.
Yeah,
Yeah, oh, scroll and see if you can increase it. Stop.
Yeah,
And wait, now we'll
Also
control and
press
scroll
cross
down.
button and see.
Huh? Now how to
Press
Control.
what to this here now, right? I know a person. Alright, so I don't know too helpful. Alright, so let me go with
The next default screen on. Now let's try like iPhone 6. Yeah, look.
You're inside, get rid of this one.
right. So we said that if we increase the intensity, right? See current going up, right? That makes sense.
Yeah.
Right. Now let's keep the intensity there, right? Let's go back to like about 4 and thing. Right, nice. So you all said now affect, let's change the wavelength, right? You all recognize wavelength values there? We can see it too good, right?
Yellow one.
But each of the different each of the different colors have different wavelengths.
Yeah.
Let's see what happens if I drop the wavelength. Let's drop it to like red. See, it changed to red there.
I guess.
Any electrons leaving?
No.
Pressure, no current. Why?
Wow.
Why it is red creating such a big problem?
It's the intensity.
Nah, same intensity. Now, watch.
Alright, ready.
If I change the intensity, watch
They
this.
have less energy.
Who say that? It have less energy. Why?
Because like then so that means it's to be slow. And then now we can have slow energy.
Very good. Very. I'll check it out. Record them. Post that. That's real good. That's a real simple explanation.
On the ball,
That's a real nice, perfect, simple explanation. So here's what he said, right? Here's what he said. Watch this here. We know this formula, right? We know that V is equal to F lambda. Right? Does the speed of a wave change? Like speed of light?
no.
Stays the same, right? Red and green and blue and black and light blue and dark blue. Same speed, right? So if the wavelength becomes larger, what will happen to the frequency? Frequency drop. But if the frequency drop, then the energy of the radiation is too small. So what does that mean? If the energy is too small, will electrons leave? No electrons leave it. That is why that happened there. And also, you were saying it earlier, E is equal to HF. And if I take off F and I put like C on lambda, I'll get H C on lambda. So we know that a bigger F gives a bigger E, right? But now a smaller lambda gives a bigger energy. So they're kind of inversely related. That's okay, Cristiano? So a big wavelength giving you small energy and vice versa, right? Right, so now if I were to make the wavelength large, what's over here? I'm gonna make the wavelength smaller. Let's go to the end there. What's that? Purple?
Yeah.
Roy G-Berg, yeah, purple. So happening now, electrons leaving. That's okay? Darian? Why that happening again? Why the current went up?
Yes.
That's how we do. Hey, tell Dumpling half an hour, hey now boy.
The car didn't even go.
Yeah, the current went up. Right, so yes, so by dropping the wavelength, we increase the energy, and therefore photoelectric effect will happen. Everybody okay with that? So some lights, some colors of light will not undergo photoelectric effect, while some will.
Yeah.
Right? Of course, that is dependent on what? How can I make those high wavelengths still produce electrons? What can I change? How can red light still produce the photoelectric effect? Anybody online can answer? Sensitive low effect. Very good, right? Thinking, right? Yeah.
I would say, in the car, he said, one of that, he bar,
Raise to the bar. Yes. So we can change the voltage. I'll explain the voltage in a little while. But what about changing the metal?
So, yeah, be inside the box and you outside.
Okay, all is kind of big. Alright. All bigger than this.
What's up?
But if we get metals of smaller work functions, then red could work. Alright? Everybody okay with that? Now last thing. Watch this here. Watch the voltage. I'm gonna make the voltage larger. Look at the graph. See what happened to the graph? The graph extending out here, right? I'm going to make the voltage smaller. You'll recognize the current getting smaller and smaller until the current is zero somewhere here. Current is zero. What does that mean?
There's no flow charge particle should be zero.
So therefore, no electrons reaching the other side. So no electrons flowing here. Online, you're with me still, right? No electrons reaching here. If no electrons reach in here, if no electrons reach in here, then no current here.
So tsunami, that down. What is it?
That's when yeah. That voltage has a special name. That voltage there, where the current is zero, we call that stopping potential. Because technically, if I put that back to zero and the electrons leaving, but the problem with the stopping potential, it stops the electron from reaching the next side. So the electrons might leave plate A, but not reaching P. That's okay? And if it's not reaching B, no electrons will flow in the circuit. Everybody okay with that? What you're observing here now is a very special graph of current versus voltage. Right? And that point down there is what we call stop potential. Yeah? Which one? Formula. So this formula is the energy of the photons, right? But remember that energy goes towards breaking the bonds, and the remaining is the actual energy leaving with. Correct? So this is the energy required to break the bonds, and this is the energy leaving with. This is the energy coming in with HF. This is to break the bonds. Same thing. This? Oh, no. That's just a definition that you have to learn afterwards. Work function is E F naught. And I'm going to explain F naught right here. You're going to see F naught here. Well, no, you're going to see lambda naught here, but I can see F naught. Right? But you allocate everything happening in this experiment here?
Yeah.
Yeah?
Yes.
All right, so that's the photoelectric effect. You all might recognize here that I could keep adjusting this. Oh wait, sorry. I can keep adjusting the wavelengths, right? Until there's a particular wavelength that nothing will happen. Let's see if we can find it now. Let's see if we can find it. 2.27, all right. Right, what you say? It's still happening, electrons leaving, right? Current reading real small. But if I go to close to this value here, 2.27, that's it. You recognize that? Watch what happening there from yellow. From yellow, nothing happening. You see that, Susanna? And the reason, real simple. I'm going to show you where the conversion comes from, but watch this here. This value here is too small because we need this value here for it to happen. Everybody okay with that? You don't have to draw this in your notes, right?
Yes.
We can do some small calculations now. Are you seeing any electrons flowing into the yellow? No, that's all. Half the pan. Because the energy too small. Energy too small. Are you okay with that? Right. Write the formula down and let's use some of the values from here now. Right? Just one small note before you do that. Stopping potential. Write this down. Stopping potential ready? Write this down now. Stopping potential is the voltage at which I just start. I know stop about that start. The stopping potential is the voltage at which the photocurrent in the circuit is the potential at which the photocurrent in the circuit is how much? Is zero. Is 0 amperes. Yep. Full stop. It stops. Full stop. It stops the electron from leaving plate A and going to plate B. It stops the electrons. It stops the photoelectrons from leaving plate A and going to plate B. Right? Remember calling it photoelectron because those are the ones leaving, right?
So the ones coming of radiation.
The ones coming in are the photons. Photons hitting the electrons and producing photoelectrons.
Now you pick it up. Now you pick it up. I wish I would.
That's fine. I don't know if they have. Somebody leave this last. Anybody remember?
Yeah,
Huh? Yeah, how about 5 on it? 5, how much?
I don't want to go into that.
How you know? I think I don't know.
I say I don't think.
All right. I'm going to show you two quick things. Can I show you which here, boy? All right, now I know this. Let's come out of this, right? Let us come out of all right, what do I do? I'll go back here. Nice. Online and follow, okay? Daniela?
So we drop it on that in physics. That's the ones here. Support us.
Definitely.
Somebody played the.
Right. Before we jump to calculations, I wanted to show you something here, right? Darian, stay quiet now, boy. I don't think you think about pronounce your mouth enough. What is here? Hello, what's here now? Hey, boy. Right. So if you look here, right, I'm going to point out a few things. Number one, H is Planck's constant.
Yeah.
And the value is 6.63 by 10 to the minus 34. Right? That's Planck's constant. Right, but here's the problem. The frequency bars that we're working with are what? What are the frequency bars we're working with? Like with those waves. Tell me the frequency of red light. Check it fast. Frequency of red light.
Frequency of red.
All right, you all might remember frequency, but remember wave? Remember wavelength?
Yeah, red light is on. It's like 10 minus 6.
Right, so watch here. So frequency is equal to speed of a wave over lambda. Right, we'll check it as now. Right, so really and truly, this formula is equal to, instead of writing F, I could write HC over lambda.
So she basically E.
So C is the speed of light here. C is the speed of light, 3 by 10 to the 8 meters per second. All right, everybody watch here. So let's say for red light, you all remember the wavelengths, right? Let's assume it's around 600, right? 600 nanometers. Watch this here. 600 nanometers. Let's look at the energy a photon like this will produce. E is equal to, H is what? 6.63 by 10 to the minus 34. Speed of light, 3 by 10 to the 8. Wavelength is equal to 600 by 10 to the minus 9. Go to your calculator and tell me what you do about that part. Huh? Okay, yeah. Tell me what the exact part. No, wavelength. No, forget that. I just change the formula.
620 to 750.
620, right? So let's change to 620. 67.
That's it. Yeah, we got it.
Yeah.
2.7 minus 8.
Right. We'll go this time away again.
3.2 by 10 to the
3.2 by 10 to the minus.
3.2 by 10 to the minus 8.
And you use 620, right?
Yeah.
See how small that value is? You see how small the value is? Yeah.
So I got 2.2
Yeah, that's right. So the problem there, Shazana, is that that value is real small. Yeah? Shazana, this value real small, you find? Oh gosh, Dario, oh gosh, boy. Dario, shut up now. This value here real small earlier. So what they invented was a new unit, right? A new unit called electron volts, right? So we have to learn to convert joules to electron volts, right? So we need to find out way to go from here to here. Real simple. To go from joules to electron volts, all we do is divide by 1.6 by 10 to the minus 19. Right? So if I divide 3.21 by 10 to the minus 19 by 1.6 by 10 to the minus 19, how much we getting?
Approximately
2.0.
06. Yeah, right.
2.000 separate
Yes,
right? 2.01. Right. What you see earlier?
So what's you?
Electron volts. If you all remember the simulation, you all remember that anything below 2.27, anything below 2.27 did not allow electrons to leave. So you all see why red light will not allow electrons to leave. Too small. So the values that we saw in the little simulation there were in this unit. Yeah, for that material. For sodium was I think 2.27. So anything less than this, nothing will happen. Everybody okay with that? So red light didn't allow anything to happen. Yeah? Because then, see how much you're doing today? When Jacob there, where's that one? Tell him. Jacob. We're talking right through. Are you okay with that? So now, when you see electron volts, you know it's converted, right? And you reached it?
Nah, really early.
You no longer have to wait on come upstairs.
Hey.
Online, you're okay with that conclusion there? Yeah? Right, so
Okay, tambah question bro guys. Itu tuan, tambah question.
they could do one else. Right, and next week now, like I said, I should run.
That's what she is.
I need to do because
Ah,
so I'm playing.
all right, actually, you know what? Before we do that, I just want to give you two more small things and I'll be able to give. Right, what you say earlier. So we learned that E is equal to HF and E is also equal to HC on lambda. This is for incident radiation. Then we learned about work function. Work function is HF naught, or I can use the same C on lambda, HC on lambda naught. Right? This is for the electrons, right? That's okay? Right. Before I move on, this F naught, right, is what we call threshold frequency. This is the lowest frequency that's possible for it to happen. Remember, I showed you all, if we made the frequency too small, the whole process won't happen. They're the smallest frequency. And then I also showed you that if the wavelengths get too big, it won't happen. This is called threshold wavelength. That's okay? So this is threshold frequency, threshold wavelength. Right? So let's make a note of that. Threshold frequency. This here is the threshold. Threshold wavelength is the largest wavelength. Threshold frequency is the smallest frequency. Right, and last thing, the kinetic energy is a half mv squared, or we could use a version of this, charge of an electron by stopping potential. Right? Because if you all remember, at the stopping potential, we sort of match the energy of the electron leaving.
So S is something that's low.
So Vs is here. Stopping potential. right? So the reason I show you all of this is that this one formula have different variations, right? Instead of writing this, I could write EVS. Instead of writing this, I could write this or this. Instead of writing this, I could write this or this. So the formula have slight variations, right? Walk the graph for next day, right? Yeah. Well, I'm plot graph. Go plot it on your blue. Everybody okay with that? So these are all the things that we need to know about fidelity plan. Right? We have a 5 minutes, so we can do a question. Let's do this part B and we done.
No, see, fine.
Well, right, but that there are 5 minutes to do. And we just doing part B and C. Oh yeah, we don't have much time. We don't have much time. Right, soon, now we up. Because I'm not put on the phone. One question. Mark, he's so good. Shut up, come to the question. So what year is this? I don't know. Put 2000 on something. Put anything you want. I'm not sure, I'm not sure. We're doing part P and C only here. You don't have much time, right? So they gave you a work function. Oh yeah, finish something now.
I write everything.
Symbolic work function. And that's sure that earlier, or I didn't write it. But I tell you that's called. All right, sorry. Yeah. That's work function. Sorry, right? We simplify. I thought what I said. We simplify. You can start by right here. Right, so that value is in what? So how do we convert electron volts to joules? multiply by 1.6 by 10 to the minus 19. How much is that?
3.52 by 10 to
Sorry?
3.52 by 10 to
Nice. Next one. How we getting threshold wavelength? What's the formula we using, Yash? What's the formula we using? To find threshold. Hey, this was not say boy Yash. What that you tell me the thing now. E is equal to what?
Yes, sir.
That one you like, if you like that kind of phone. Yeah. HC on lambda. HC, but
But that will give you threshold wavelength.
HC on lambda not.
Yeah, they rearrange it.
Right, well, you gotta use that formula to rearrange it. Right, so lambda naught is what? Lambda naught is HC over energy. And we have H, we have C, and we have the energy.
Where are the H?
6.6
Constant.
Where are the E?
We found it on what was lambda naught?
Oh. What's C?
Huh? 3 by 10 to the 8 boy. What you all got for lambda naught?
I get what, but yeah.
5 point 5.6 5.65 by 10 to the minus 8.
Minus 7.
No, it should be minus.
I don't know. Come on, trust me, trust. It's not minus 7.
Anybody online? What you all got? Minus what? Minus 7 is that? 7.
But
Minus 7, okay. 16 I get minus 7. So they get. Last one. Yash, what's up talking to them now? Yash,
Them.
part 2. What's the maximum energy of the photoelectrons when the metal is illuminated by light of that wavelength? E is equal to what? HF, well, we do have F. Very good. What's the lambda we'll be going to use here? 4 times 10 to the minus 7. Anybody can help me out? What again? Anybody with the calculator can help me out there, please? Sorry, sir?
What's C is? Yeah, right? What's C is?
Stop in the middle. Stop in the middle.
So wait.
Look it on the board, Dario, and 3 by 10 to the you have to convert now. So what can we talk?
So I guess 4.97.
How much? 4.97 by 10 to the minus 19. Anybody else get that? Please? Very good. Same thing? Alright, nice. Last part, stubby potential.
I already done this.
Last part and we done. Oh, how we finding it? We had a converter.
No, that's rejection.
Remember, I told you the formula for kinetic energy could be varied. Right? So we're using energy being supplied is equal to the work function plus EVS. So EVS will be energy supplied minus the work function. That's the formula you told me, friends, at the beginning of the class, remember?
Yes. So, so what do you want?
All right. Right, so tell me what you're gonna please. 4.97 by 10 to the minus 19 minus 3.52 by 10 to the minus 19 all over E, right? All over E. Tell me what you got, please. How much is that? Wrong. Right, so we'll do more of these past equals the next day, right? Same formula here.
Oh, but it looks different.
It looked different because instead of writing kinetic energy, I wrote EVS. Remember I told you that's it. Not wrong. Anybody work it out? 0.91. Right, 0.91. So next day we'll do a lot more of these, but you'll follow the concept.
That's it, sir. Understand this one. We have done one, but we do lots of it. So that's not.
That was the open thing.
Last class was.
The open thing. Yeah, I know it. That we didn't work out.
That's all.
I was about the open thing, right?
We take out some of that.
No, I'll do that back because last week that merger thing didn't work out.